All right, so problem 6. This is the standard thing where we're going to have a pulley. Let's have mass big M here, mass little m here. Just see, second semester, we're actually going to learn how to account for for lack of a better word, the circularity, the roundness, the wheeliness of the pulley and its mass when we study rotational motion. And it's going to complicate this problem a little bit, but for now, this is a good first approximation to this problem, and it's definitely a worthy problem for an AP exam. You'll actually see both versions of this problem. And we're just doing the one that deals with forces, obviously, since we haven't got to rotational motion yet. So when we draw our free body diagram, we'll have a tension going up. We'll have the weight of big M due to the Earth. And then for little m, we'll have an identical tension going up and weight of little m due to the Earth. And we're going to assume a sign convention that favors the heavier or the more massive object here. And so when we set up our equations, remember any force that goes with this sign convention is positive. Anything that opposes this sign convention is negative. So I'm going to kind of skip a little quickly here and write this as mg minus t equals big M times A, and then t minus little mg equals little m times A. So I'm skipping some free body diagram to equation steps. Now we want to know the acceleration of the block, so why don't I go ahead and isolate that on both sides. So here we go. I'm going to do the following. Mg minus t over big M equals t minus mg. Actually, that's to get the tension. Let's do something else. Let's isolate tension on each side. So I'll have mg minus ma equals tension for the top equation. And then mg minus ma equals t. And then here we have mg plus ma equals tension for the bottom equation. When we shove these two equations together, we're going to end up getting mg minus ma equals mg plus ma. And let's do a little bit of isolation. We're going to have m minus little mg over big M plus little m equals a after we do algebra. So that then gives us here choice E. Now for number 7. So I'm going to say I skipped some algebra here just for number 6. Sorry. Now for number 7, let's draw a free body diagram. So we're going to have the force pushing the block into the wall. We're going to have the normal on the block due to the wall. Friction holds it up. Weight wants to drag it down. So we've got a couple of equations here. Friction balances the weight, and we know that the pushing force balances the normal force to keep it from falling. Now what we're going to do is figure out what this pushing force needs to be to keep the block from falling. So we know that friction is mu times n. We we also know from this equation that friction is mg, so we have mg equals mu times n. We isolate n by dividing by mu, and so what we end up getting is that the normal force is mg divided by mu, and since that actually balances the pushing force into the wall, that means the force we need to push the block to keep it from falling is equal to the weight divided by the coefficient of friction. Now for number 8, we throw a projectile into the air. There is no air friction. Point Q is the highest point in the path. We want to know what the acceleration is of the ball at Q. It is downwards. And let's be really clear, if we wanted a number for this, the downward acceleration of the ball at Q is in fact G. Just to be clear. At point P, same thing. The only force that acts on the ball is mg, is its weight. There's inertia of the ball. It's thrown horizontally, so that speed carries, its inertia carries it forward. But the only force that's actually acting on it is the downward force of gravity. And number 10, a block of mass m is accelerated across a rough surface. That means we have friction. We want the acceleration of the block based on the knowns that we have here. So this is F. We have friction here. And let's actually draw a full free body diagram. So I'll have F. I'll have weight equal to mg. I have the friction force here that's a given. I have a normal force pointing up. Now let's talk components. I'll have F cos theta here and F sine theta here. So let's balance our forces. Well, we're accelerating, so we have balanced and unbalanced forces. So horizontally, we're going to have F cos theta fights the friction, and the effect is that the block accelerates. So if we're just looking for an acceleration, this is what we get. If we want the coefficient of friction, let's do it a little step at a time. So I know N plus F sine theta balances the weight so that we have no acceleration in that direction. So the normal force is F sine theta, the normal force is mg minus F sine theta. And so the friction, so if we wanted the coefficient of friction, and we know that friction is mu times n, so we're going to take this friction force and divide it by the normal force here to get mu. That's going to give us F over mg minus F sine theta. And that's how I'm getting choice E is my answer for number 11. In the next video, I'll take a look at questions 12 through 15.